welcome all to our CSIM e-seminar. We are very happy to have Professor Lionel from both the School of Electrical Engineering and Computer Science at the University of Ottawa and the SNT Center for Security, Reliability and Trust at the University of Luxembourg. Professor Briand is an IEEE fellow, very widely known, okay, and with several grants, a wide experience, both, well, mainly at academia, but with strong collaboration with industry and with very successful projects, a large amount of awards, okay, and from societies and from conferences. With one word, okay, he is one of the best researchers that we have in the area. We are very happy that he accepted our invitation. It is our honor to have you here, and I should also acknowledge the great work of Burak, who helped in the setup of this seminar. So, with no more words, okay, Professor Briand, thank you again for accepting the invitation, and we look forward to see this interesting seminar. For the people attending, you can write your question at any time, and at the end of the session, we can you can ask them directly, or we can read them for Professor Briand. So, Lionel, thank you again, and the floor is yours.
Thank you. So many thanks for the invitation. So this presentation is an attempt at conveying my personal perspective on how to ensure that machine learning enabled systems are trustworthy. This is based both on my experience, a number of projects, and my reading of the literature. It's, of course, this is an overview, not a detailed technical presentation, given that the audience is not specialized on those topics. So let me give you a bit of a context and motivation first. So what are machine learning enabled systems? Those are systems that contain components, for example, in the perception and control layers of cyber physical systems, components that have been developed using some form of machine learning, for example, deep learning, other kinds of machine learning. And that changes a lot of things in terms of assessing and analyzing the dependability of systems, because as you may know, those components are not based on explicit specifications and code. There are many domains where those components are increasingly present. For example, in the automotive domain, you have applications like object detection, identification, sensor fusion and scene comprehension, driver monitoring, even to some extent driver replacement, various functional safety or security aspects, and even the control of engine, the powertrain control, for example. So those ML components are increasingly part, as you can tell, of safety and mission critical systems, and in an increasingly large number of domains, using very different machine learning algorithms of different kinds. But most particularly, what I will be talking about today is the particular case of deep learning components and a little bit reinforcement learning, which are techniques that are increasingly used for such functionalities. So the question is that when we use such components, how do we minimize the risks? How can we help, therefore, with things like safety analysis? And this requires that we clearly identify situations where, for example, deep neural networks fail, and whether those failures are acceptable. And if necessary, devise countermeasures, which may involve retraining of, for example, the deep neural network, or wrapping up the deep neural network with some form of safety monitor, for example. One way to assess how trustworthy those systems are is to use online testing. So in online testing, basically the system is in a feedback loop, for example, with a simulator, and try to simulate scenarios in order to guide the system towards safety violations. And that's one very common practical way of assessing such systems. However, there are different testing levels. Even though testing in all those contexts is the main mechanism through which we gain trust, there are different types of testing that need to take place. We may test the model in isolation, for example, the deep neural network. We may test its integration with other components and other models, or we may test the entire system. The research is largely focused on testing those models in isolation. However, integration and system testing is also extremely important in practice. And as we will see, it requires different automated approaches. Another aspect which is important is what information do we have access to? Do we only know the model input and outputs? Do we have access to the training and test set that were originally used? Or do we actually have access to the runtime state, for example, the neuron activations of the deep neural network, the hyperparameters, the weight and biases of the network? And this is important because in practice, when people are testing such models, they don't always have access to all that information. Very often, the models, for example, that automotive companies use come from third-party providers that are specialized in machine learning. Also, there are different objectives for testing. Of course, if you test a model, you can test how correct the classification or predictions are. But you may also want to test the robustness, either to noise, because sensors are noisy, or attacks. Fairness, you want to make sure, because you may probably have read about that the problem with machine learning is that it learns biases from the data. And actually, that's a problem in many applications. So fairness is another, for example, objective of testing. And you may want also to assess the efficiency in terms of learning and prediction, which may be important in some application contexts. And of course, when you find failures, there can be many root causes. It can be imperfect training, for example. The training set is incomplete, overfitting. The hyperparameters of the model have been poorly selected, or the model structure itself is not adequate for the problem. And when you test, the challenges is that usually the input space is very, very large. You have many safety requirements that you need to test for. If you use simulation is usually computationally intensive. And as I said before, sometimes the models, you don't have the internal information about the models because it was provided by a third party. For safety analysis, if you take the example of road vehicles that are regulated by an ISO standards, and there is actually a standard that is focused on those functionalities that are supported by machine learning. It's called safety of internet functionality. They rely, of course, on accuracy evaluation of the models based on inputs generated by simulator or collected in the field. And in the end, they rely on manual inspection of error-inducing inputs, for example, error-inducing images, in order to identify the root causes or what could be the root causes of those prediction errors. And then based on that, people try to identify unsafe scenarios and then improve the system and try to demonstrate that those unsafe scenarios, for example, are very unlikely or that somehow errors in that case are acceptable. But there are many open problems with that practice. is that first, it's error-prone and expensive to analyze a large number of inputs, error-inducing inputs. Imagine looking at images and try to understand what they have in common. The manual inspection of additional inputs to retrain the DNA in order to improve it and make it more robust to those error-inducing inputs is expensive. And you may have underrepresented unsafe scenarios that you may not notice because there are only a few instances in a large number of inputs. So, of course, people in the past have worked on techniques to try to explain what happened in, for example, DNN's classification of predictions. People have used, for example, heat maps that capture the extent to which pixels in an image impact on a specific result. But there are many limitations. Heat maps need to be, again, manually inspected. And again, you can miss underrepresented failure causes. And debugging is not automated. I mean, trying to improve the model. So if we go into more detail about the challenges, there are a number of challenges I'm going to go through, one at a time. So first, the input space, as I said before, is very large. Imagine you have inputs that are images, text, any number of different types of inputs. All of those usually are defined on incredibly large input spaces. So, for example, the Tesla autopilot collects data from several front, rear, and side cameras, a radar, and 12 ultrasonic sensors, for example. And then there is, each time you need to execute a test case, there is a cost of test execution. If it's based on simulation, for example, it can be extremely expensive. And then when you test, you need to know what is the correct output. For example, if it's a classification, what is the correct class? So you need to label inputs. And as we know, labeling cannot be automated in many circumstances, and the labeling cost is quite high. So if I take again an example, an automated emergency braking system, where you have a sensor that detects an object position and speed, and a vision camera that determines whether if there is in the field of view of the car an object, whether it's a pedestrian, the input-output domain here is represented as a class diagram, and you have many aspects, such as trajectories of vehicles and pedestrians, the weather condition, the road topography, the scene light, and many other things. So you can imagine that if you want to understand how trustworthy such a system and you want to test it, you are handling an extremely large input space. Moreover, there are different kinds of inputs, adversarial input and natural inputs. Adversarial inputs are focused on testing the robustness, for example, of the system or the model, and they try to capture noise or attacks. And natural inputs focus on functional aspects. They correspond to actual real scenarios, normal scenarios. And adversarial inputs, adversarial example is something that you probably have heard of, but people have noticed some years ago that sometimes applying an imperceptible perturbation to an input, for example, an image, would arbitrarily change the DNN predictions, for example. So the problem is that people expect their models to achieve a certain level of robustness to such noises. So it's easy to test with adversarial inputs because by definition, the prediction or the classification is not expected to change. So you just need to make sure that nothing changes whenever you introduce noise or introduce an attack. And there are many techniques on which this is based on image processing, image transformation. But the problem is with adversarial inputs is that if they are not realistic, and then you have to define what realistic means. If they are not realistic, then of course your system or model may not be robust, but it may not matter, So that's really the problem with adversarial inputs. For natural inputs, focus on functional aspects. Of course, they should be realistic, but they suffer from the oracle of relic problem is that when you generate a new input, what should be the predicted output of the classification? I've talked about that before. So people have tried to test, for example, images taking, DNNs taking images as inputs by applying label preserving changes, for example, by making weather condition transformation and stuff like that. But what we really need to test in practice is not just single inputs for many of those systems or single images, and we cannot just focus on label preserving changes to existing inputs. We need to account for the impact of object dynamics, for example, in an automotive system, the car speed, in different scenarios, for example, different configuration of roads. And so we need to test scenarios. There are very limited solutions that exist, and this is a problem for safety and for even complying with a safety standard, such as the standard I mentioned before, the SOTIF standard, where that requires, for example, in-the-loop testing of relevant scenarios in different environmental conditions. And there are different types of testing then, as I've briefly mentioned before. You have offline testing where you just feed inputs and you check the prediction error, and you have online testing where you have a feedback loop, for example, with a simulator, at least with the environment or a simulator of the environment. And you are running an entire scenario over a period of time. And for me, in many cases, I've said offline testing is just not adequate. So you can imagine you cannot properly test an advanced driving system that way. But of course, online testing is much more difficult and expensive, but it's required in order to find safety violations, because somehow it accounts for physical dynamics and cumulative effects in cyber-physical systems, for example. And so usually when you do that, you need to do that with a simulator, because you can imagine it's not very practical to do that with, for example, an actual vehicle in the actual environment. And there are a number of simulators that exist at different levels of fidelity and control. And basically then a test input is a configuration of a simulator, and a test output is a timestamp, a set of values telling us the status of the ego vehicle or the other vehicles, the pedestrians, whether there was a collision at any point in time during the simulation. And of course, simulation comes with challenges as well. Is how do you effectively guide the simulator towards safety violations? How do you effectively basically explore the input space? Because simulation often is expensive. And also, you have also always the issue of the fidelity of simulation and the impact of such fidelity on your results and analysis. Another question regarding to testing is when is it good enough? When have you tested enough? So the goal is to assess what people call test suite adequacy and to guide test selection so that it's as effective as possible within a certain time budget that is available. And so what we want is somehow devise minimal and fault-revealing test suites. So people, for example, without getting into details, for deep neural networks, have defined so-called structural coverage criteria, where they monitor the execution of test cases and they check the activations of neurons, for example, in a neural network, and they check to which extent these neurons have been activated and exercised during testing. And there are a number of different coverage criteria that have been defined that are supposed to indirectly measure somehow the completeness of testing. The problem is that, of course, this requires access to the internals of the deep neural network at runtime, which you cannot always do in many practical settings. But also, many studies have shown that there is a weak correlation between such coverage criteria and actually the probability of misclassification how bad predictions are for natural inputs. Another issue is that when we go at the system level, we're not just interested in misclassification or the square error of predictions. We know that machine learning model, no matter what you do, will always come with a certain degree of uncertainty, because training can never be complete and universal. There are always corner cases that you may not have trained the model on, so it's impossible to have any form of certainty with, for example, deep neural networks. And therefore, what is a failure in a machine learning enabled system? And what does that mean? The failure is not just a misclassification, because we expect a system to be robust to machine learning errors to some extent. I mean, at least they should be. At the system level, a failure is a requirement violation, for example, a safety requirement violation. So for us, a failure at the system level results from both a misprediction or misclassification and the effectiveness of the countermeasures you take to make your system robust to such mispredictions. For example, safety monitors. So if I take an example and you have, let's say, a deep neural networks used for key point detections in a face. For example, if you have an internal camera in a car, and that is, for example, doing face recognition to start the car, or trying to detect drowsiness of the driver, for example. And of course, the goal of testing is to find test suite that cause the DNN to poorly predict as many key points as possible within a certain time budget. That's what testing is for. And also analyze the causes, of course, of those mispredictions. But of course, you can use alternative key points on the face for doing the same thing. So if you know that there is a shadow on a certain part of the face, you use another subset of key points. So the fact that you mispredict the key points within the shadow is not necessarily a problem. It's not a system failure, because you have a mechanism to deal with that. A mechanism that decides which key points to use in order to, for example, predict drowsiness, recognize a face. Functional safety requires to assess risk in a realistic fashion, to account for the condition and consequences of failures at the system level, and decide whether the uncertainty associated with a machine learning model is acceptable. And for that, people need automated support. It's not something that people can do manually. And that's the type of stuff we have been working on that I'm going to briefly present next. So research directions, examples of projects I've been working on and trying to draw conclusions from that. But of course, there is a large literature, so this is very much a personal perspective. So for example, the most straightforward thing is evaluating and selecting test suites for deep neural networks, therefore at the model level. And the objective is to explore the space of possible DNA inputs and understand what are the unsafe parts of the input space. And in our case, on the project, we work on a black box approach, because we were working with General Motors, and they told us that very often they don't have access to the internals of the deep neural networks, because very often it comes from the third-party providers or other divisions of GM. And so the idea is that the basic intuitive idea is that we assume that the more diverse a test suite, the more likely it is to reveal faults. But the question is how to operationalize that. Here we focus on images, DNNs that use images and input. So the technique is based first on using a convolutional neural network that has been trained on the huge data set, the ImageNet data set, in order to extract features from images. And based on that, we use a feature matrix of each image in order to compute what we call the geometric diversity of images in a test suite. And I'm not going to go into details, but if images are vectors into the feature space and you compute the hypervolume of which is within those vectors, you have somehow a measure of diversity. But of course, you need to have a measure that also scales with a large number of images and a large number of features. There are many details. And of course, we checked whether that measure of diversity correlated somehow with faults that could be identified in the DNN. And there are many, many technical details and issues I'm sparing you here. And if we have a good measure, such a good measure of diversity, we can use that to somehow select tests driven by diversity in order to minimize the number of tests while maximizing their fault revealing capability. And so we use a form of multi-objective evolutionary computing because we have two objectives. On one hand, we want to maximize the uncertainty level of the test inputs. We use a Gini index for each technique because it's a classification here. The models classify to measure the level of uncertainty of inputs. But at the same time, we want those inputs to be diverse. So we use a geometric diversity. So basically, we do a form of Pareto font optimization based on the Gini score and diversity index, or geometric diversity index, in order to select an optimal test suite. Now at the system level, where, for example, in the context where we do simulation-based testing, this is another aspect that I've mentioned before. Here, the objective should be to effectively and efficiently explore the space of possible system scenarios, again, in order to identify the unsafe parts of the scenario space. And it requires a simulation with sufficient fidelity. And basically, scalability here is, or the scalability of testing is driven by the simulation cost. So if I take first a very simple example, which is not very telling, but I'll have a second example after that. Again, referring to the key point detection example I've mentioned before. So I've mentioned that before, we use a DNN to predict key points on a face. It can be from an internal camera. And we use a simulator to generate faces with the shadows and all kinds of things. And of course, we try to assess how accurate our DNN is at predicting those key points. And an example application, for example, is the drowsiness or gaze detection. And each key point may be important for safety. And so each key point leads to a requirement that must be achieved by the deep neural network. It's a test objective. So in that example, we had 27 key points on the face, so 27 requirements and test objectives. And therefore, we have a many objective. We need to use a many objective search technique based on evolutionary computing. Because our goal, of course, is to try to make sure we mispredict as many key points as possible. And we use a so-called, as I said, many objective search algorithm, without getting into detail, that has been tailored for that problem. And so we have an input generator that is based on search, that search algorithm I told you before. We have a simulator, then that generates the corresponding image. The DNN predicts the key points, but because we have a simulator, we know what the actual key points are. We can somehow predict how close or the extent to which how close we get to violating our requirements on those 27 key points. And based on that so-called fitness value that measures how bad are the requirements violations, we guide the search further and we iterate and explore the input space that way. And hopefully we detect the most critical inputs in the different parts of the input space. So we had a number of results. We found a lot of problems with the DNN. This was a DNN developed by one of our industry partners, again, in the automotive domain. But of course, not all predictions are failures. Sometimes, for example, you have shadows, you have points in the shadows. There is no way the DNN can predict those key points accurately. And this is very often the case with DNN. They all have limits. You cannot expect them to predict everything under any circumstances. So, not, again, all misclassifications or mispredictions are failures. So you have to be able to identify that. But still, we found, by doing some analysis that I will show next, we found that some key points were underrepresented in the training data because they were often hidden, for example, by shadows or because of the position of the head. And also that there were certain things that were harder to learn that needed more training, like because the shape and size of the mass varied quite a bit, across images, and more training was actually needed for the key points around the map. And the way we identify that is that we use some form of machine learning or regression trees in order to identify the conditions under which there were severe mispredictions of the key points. And so we could identify, very precisely the conditions under which those mispredictions happened. And this could be, of course, this was a very useful source of information for people to perform risk analysis and therefore safety analysis. So we could identify clear rules leading to high probabilities of mispredictions. Another example where we were this time testing an advanced driving system with a simulator in the loop. We actually use an adaptation of reinforcement learning for testing this time. So we haven't used, like in the example before, evolutionary computing. We've used reinforcement learning agent in order to guide the simulator towards safety violations. Why? Because here we needed to do some form of online testing. We needed basically to go through a sequence of actions leading to safety violations. However, there were a number of complications. We had many objectives because we had many safety requirements. So we needed to find safety violations for many safety requirements at once. So we needed to have a form of many objective reinforcement learning algorithm that worked for our problem. And what that means is that context use reinforcement learning to guide testing, for those who are a little bit familiar with reinforcement learning, is that we consider the vehicle in the front of a car as a RL agent that aims to cause the ego vehicle, the vehicle we control, to violate the safety requirements by performing a sequence of actions. So, for example, the state of the environment from that perspective can simply be the distance between the two vehicles. And the actions that the ego vehicle can take is turn left, right, increase or decrease speed. I'm simplifying. And the reward is a likelihood of violating a safety requirement, for example, getting too close, having the ego vehicle getting too close to the vehicle in front. And of course, I assume here that you're a little bit familiar with reinforcement learning. Otherwise, I apologize. Safety analysis. So here, the objective I already explained is to identify the conditions of critical failures. For a simulator, those conditions are defined in terms of configuration parameters. For real images, it's in terms of the presence of concepts in images. And this is required for risk assessment, as I've mentioned before. But again, people need automated support for doing that type of analysis. So the current practice is very manual. I've already mentioned that. And it's very error-prone and expensive. So we developed a technique. In fact, we developed many techniques over the years, but this was the first one, where we rely on hierarchical agglomerative clustering to identify distinct root causes of DNN errors. This, of course, happens after performing testing. Okay, and we used the heat maps of the internal DNN layers because we are talking about images here. So I'm talking about heat maps, inputs are images, and use also that information to automatically retrain the DNN. So if I take an example where, for example, we try to do a classification to understand what is the angle of the gaze of the driver, according to a number of finite classes that are visible here. And this is an image input, and this is a heat map that shows where the pupil is in the image. And our technique called HUD basically rely on heat maps on different layers of the DNN to generate clusters of images leading to failures because of the same root cause. At least that's what we want the clusters to be. And then this enables engineers to ensure the safety with introducing, for example, countermeasures. So people are expected basically to inspect a small number of images within each cluster and identify their commonalities in order to understand the root cause of failures for at least images within each cluster. Or in practice, the technique is a bit more complicated. This was an overview. There are many details, and you can do clustering analysis for different layers of the deep neural network, and you have to determine which one is the best layer to do that. So there are a number of details. And of course, you have to use some algorithm for heat map generation. In our case, we use layer-wise reference propagation and some specific clustering algorithm that is somehow adequate in our context. For example, where we don't know what is the number in advance, what is the number of clusters. Then we automatically retrain the DNN by selecting new unsafe images belonging to each of the identified clusters. So this helps addressing the problem at a reduced cost. So we have a strategy in order to sample or generate new images for different clusters, and then retrain the DNN according to that. So for example, in our case study, we identified 3 types of problems. Borderline cases between 2 classes. Here, there is nothing really you can do. Borderline cases are inherently hard. You can just do more and more training of those borderline cases. Incomplete training set on the right side, that's the most obvious. So for example, we didn't have many images where the eyes were nearly closed. That's a form of corner case, if you will. And also we were missing a class actually, where the driver was looking, the eye of the driver was in the middle center. The gaze of the driver was in the middle center. We forgot that class in training the classification model. So this analysis helped us identify what were the problems, and this is a simple example, but in practice, of course, it's a bit more complicated. We developed a similar technique called SAFE that is black box. HUD is white box. So it's black box is based on feature extraction and dimensionality reduction, where we try to do the same thing, but in a black box manner, and we got actually very good results. It has many practical advantages. You don't need to modify the DNN to enable LRP. We have reduced training time in memory, and we even have more actually accurate clustering in there. What time is it? Let's see. Oh yes. So yes. So I'm going to skip a couple of things. I'm not sure how much more time do I have. Because
I think we can use another, let's say, 10 minutes or so, or 5 to 10 minutes.
Okay.
Yeah. Mm-hmm.
So very briefly, I'm just going to cover very briefly something. At the system level, as I said, we know that machine learning models are inherently uncertain. And so what we really want to understand is with the robustness and the mitigation mechanisms in the systems. So what we want to learn as accurately as possible is when a machine learning set of inputs and outputs lead to system safety violation at the system level. And so we have developed a technique to do that. I won't have the time to go through that. But here the goal is different. It's to tell the user, when those conditions are true on the inputs and outputs of your machine learning component, that particular safety requirement is going to be violated. So you have to do something. Either you have a safety monitor that monitors for that particular condition, and take some kind of corrective action when it happens. Or somehow you have to retrain your model for those situations. Another issue is that I told you that simulation is very expensive. So in practice, when you do such testing analysis, you want to minimize the cost of simulation. This is very, very important in many domains. So what we try to do is to build surrogate models for the simulator. That is to try to understand when we can predict the output of the simulator accurately and use rather that surrogate model rather than the simulator. Of course, it won't be 100% of the time, but as you simulate and acquire more simulation data, you can build such surrogate models. So of course, they may not be as precise or as accurate rather as the simulation itself, but they save a lot of time and therefore they make testing much more efficient and therefore also much more effective. So that's also something we have done. We have developed techniques in order to efficiently and effectively build such surrogate models and integrate that into our testing strategy based on evolutionary computing. So now let me conclude that we will have some time for discussions. So automated testing, there are different levels. As I said, we need different automated solutions at the model integration system level. I haven't covered everything, but you have seen example at the model level and the system level. Automation is key, and it's different for those different levels. We have used strategies based on evolutionary computing and machine learning as well to automate that. Scalability always remains the main challenge. We have seen one technique to do with scalability, which were very briefly surrogate models. And in the future, we need not only to test stateless models like deep neural networks, but we need also to focus on things like reinforcement learning as well. And I have actually a student who has been working on this and who has already obtained some interesting results. For safety analysis, we need automated strategies to identify the root causes of error-inducing inputs, and we have developed such techniques recently, at least when inputs are images. They are based on feature extraction, dimensionality reduction, and clustering. Similar strategies can be developed for other types of inputs beyond images. We haven't done that yet. We have to deal with also situations where you have real inputs as opposed to simulators. You have different techniques to support that. We have seen also how we developed, well, no, we haven't, but I've mentioned it briefly, automated testing strategies for model retraining based on root cause analysis to efficiently reduce risks. Thank you very much. Thank you for your attention.
Well, thank you very much. This was really a great talk and really very informative. It's really appreciated. I thank on behalf of all the CSIM members once again. So Nizar had to silently leave. So I'll be moderating the rest of the Q&A sessions. If there are any questions from the audience, I'll be happy to convey them, or you can unmute yourself. I see Murat is raising hand. Please go ahead.
Thank you, Burak. Thank you, Professor, for your beneficial presentation and information for all of us. I have a question for you. As far as I know, the number of inputs directly affects the complexity of search space. That's why my question is, what is the best strategy if the number of inputs is high? The problem has high dimensional inputs.
Yes. Well, the way we work is that, I mean, I know I haven't been through the details, but what we do is that we use a mix, or what we have done in the past, we use a mix of evolutionary computing and machine learning in order to guide the exploration of the space towards safety or violation of requirements violations. So usually that means that if you use evolutionary computing, you have some form of fitness function that tells you how far you are from violating a requirement. And you can combine that with machine learning in order for the machine learning to try to predict the parts of the space that are the most interesting to explore, on which you should focus. So usually we develop techniques that way that make the exploration of the space much more efficient. And beyond that, of course, you can use the usual techniques of dimensionality reduction before that. But this is nothing very original. But that's what we have been using.
Okay, thank you so much for your answer.
Thank you very much. Do we have any other questions from the audience? See.
And by the way, just to briefly mention, there are people who have been working on completely different approaches. Basically, namely formal methods or informal methods to analyze DNNs. But the problem with those approaches is that they are very limited in terms of the type of properties you can check. And they are also very limited in terms of the size of the deep neural networks they can handle. So in the end, they are very, very far away from being practical or applicable, except in cases that are very artificial. So, and of course, those approaches, they are not based on smart sampling. So a priori, you might say that they do not suffer from the high dimensionality of the input space, but in practice they do, because they can only handle very small models. And again, they can only focus on certain type of properties. Whereas, in our case, we want to be able to check any type of safety requirement, for example, that people are interested in.
I see. Thank you. Let me see. Oh, okay. Murat has another question.
Yes.
Okay, I was going to ask my question.
Yes. I have another question because the surrogate modeling and optimization is my PhD topic. That's why I would like to ask a question about surrogate modeling. Do you need special accuracy for surrogate-based modeling to test the system?
What we need in the end is surrogate models that predicts the simulation output as accurately as possible. That's what we want. And we have tried a number of techniques. I'm not going to go into this. I'll share my slide. There are references. You can look at them. But that's what we want in the end. And we want, of course, also the surrogate models not to be too expensive to build. That would defeat the purpose. So basically, we have looked at many techniques and many trade-offs. And the two trade-offs is this: how accurately we predict the output of the simulator, and it doesn't need to work all the time. We just need to know when it works. Okay. If we know we cannot, we just simulate. But if we can save 50% of the simulations, it's nice. So the trade-off is between the accuracy of predicting the simulator output and the cost of building the surrogate model and updating it.
Yeah, thank you. Thanks so much. That's all, Burak.
Yeah. Okay, thank you. So in the meantime, maybe I can ask one question in my mind. So about automated testing and machine learning enabled systems. How to incorporate, that's what I'm wondering, how to incorporate the concept drift into automated testing.
Incorporate what, sorry?
The concept drift.
Sorry.
Oh.
The what? Sorry.
Concept drift. So,
the concept drift. Okay,
exactly,
sorry.
yeah.
I haven't looked at that. I haven't thought about that problem. It's true that some of our techniques are based on concept extraction from images.
Yeah.
The black box approach to safety analysis, for example. I'm not sure actually. What do you have in mind in terms of the problem? Because I haven't thought about this. What goes through you? You have something in mind? Tell me more.
Yeah. Like, for example, behavioral analysis when machine learning models are introduced into like continuous authentication or behavioral analysis kind of things. That's what I was thinking, how you know, concept drift can be also incorporated into testing. Yeah.
Yes.
Yeah. I mean, I haven't thought about it before, but while I was yeah.
Yes,
Listening to your
basically,
presentation,
it's
it came to my
like
mind.
testing a constantly evolving system with evolving deep learning models, basically. I don't know what is the impact on what we are doing. My guess is that that requires to do testing on a regular basis, to redo testing on a regular and safety analysis on a regular basis. But then in practice, the question would be how frequently or how often do you need to do it? You know?
Yeah.
Because obviously people have limited budgets and time, so they cannot continuously test their system.
Exactly.
So we need somehow a strategy to decide when it's worth it, redoing the testing and analysis.
Exactly.
I haven't worked on that. It's a good point.
Yeah. Thank you. I see another hand raised now. Ömer, please go ahead.
Yeah. Thanks for this great webinar, Dr. Bryant. We are dealing some problems, some machine learning problems, and in fact some UAV-enabled robotic network problems. And sometimes we deal with not training salesman problem, even combined with training salesman problem with other problems like knapsack problem, even more complicated than. And when you consider such MP hard or even more complicated problem than MP hard problems, can we suggest some trustworthy machine learning techniques? We may apply deep Q learning or some other techniques to solve these problems. But when you also consider our aim to catch the low latency in the 6G era, we need some robust solutions. So what do you think about that? Theoretically, we can propose some kind of optimal structure, but when you consider that in practical manner, in low latency manner, robustness, fairness manner, low latency manner, can we propose such machine learning techniques, some trustworthy machine techniques? It may be a general question, but I wonder your ideas or thoughts.
I'm not sure I grasp the entirety of your question. It's a very large question, but I'm not sure if you are trying to get at how to measure trustworthiness or how to get guarantees about trustworthiness or regarding the complexity of the systems you are using in robotics or no. That's actually the point. The techniques I've been working on, they work on such complex systems, as opposed to formal methods, And that's the whole point. We try to build techniques that scale and that are not affected by such complexity. But of course, there are always limits.
Because when you consider 5 nodes, it may be okay. But when you consider visiting a 10 node, training assessment problem with 10 node or more, maybe 20, it is a bit harder than normal. That is why I wonder that.
What did you say? What did I say? Sorry,
I just say that we also look for some scalable solutions when you consider robustness, and can we suggest some robust solution, some scalable solution?
Yes, that's the whole point of what we are doing. That's why we use techniques that are based on evolutionary computing and machine learning to efficiently and effectively explore the input space and identify, rather than providing guarantees, which is not possible, is to help people identify what are the areas, the input space that are unsafe, and then let them understand how those areas are characterized so that they can assess the level of risk, and see whether they're acceptable. And then use those outputs to retrain and therefore make the model more robust as well. So, that's exactly the objective of what we are doing. You are trying to come up with scalable, robust solutions. And so far we haven't encountered an example where it didn't work, but we might someday.
May I ask another question? Just one question, Dr. Burak?
Yes.
Sure, please.
Okay. Also, sometimes we deal with some large size data samples. For example, it has even a 3 million size. Just for example, we take some samples for wireless signals. We take samples for 1 day, and it is 3 million, 5 million, and instead of working with 3 million size, we plan to work with the reduced size. For example, maybe 300 to 300,000 or that. But is there anything? I just wonder, how can we decide which size should we work at? So because when I consider trustworthy, it is also we try to explain our motivation, our intuition to decide that. Of course, we expect a good result, but also we try to explain that. And how can we decide to amount of reduction, the data size reduction?
Yes.
Is there any technique?
Actually, I have briefly talked about that during the presentation, and we have done some work on that. Remember, at some point,
Maybe I miss.
go back. No, but it's normal. There is a lot of information, and it's very hard to. But you remember at some point where I talked about getting a reduced test suite that is fault revealing, and it's exactly about that, because also for in many case situations, inputs are not labeled, so you have to label them yourself. So obviously that limits the number of inputs you can use, that's where we used that technique based on geometric diversity and trying to find a measure that is correlated to the number of faults that you detect in DNNs, and then combine that with some form of evolutionary computing algorithm in order to find subsets of a certain size that maximize geometric diversity and uncertainty in terms of the Gini score, because in that example it was the DNNs were classifying. And then people can choose, one of the subsets of a given size on the Pareto front, and the goal is to maximize the probability of misclassification and misclassify the diversity of those misclassifications at the same time. So you say, I want 500 inputs, what are the best 500 inputs? And that's what this does, And then you have to label the 500 inputs, or you have an automated way of labeling them, but in many cases we don't. In many cases, that's why we need to deal with a limited number of inputs. It's because of the labeling effort. In fact, there are many companies now in many domains who sell labeled data. That's a business because it's such a cost.
Well, thank you very much.
Thank you very much.
I'm looking at the time. We have already passed 2:30. I'll take the last question from Furkan. He typed this question, but I'll let him directly ask his question to our speakers so that they can maybe interact. Yeah, please go ahead.
Thanks for the presentation. How can you detect a trained model whether it is hijacked to not to detect a specific situation? For example, like it detects all the faces, but it specifically doesn't detect one person's face. So is there a way to test this kind of systems?
Well, if you know what could be the source of the problem, what are potential sources of the problem in that face, like someone wearing a mask or someone putting her hand in front of her face or something like that, it can be part of your simulation. Actually, we have worked on that. We have worked on testing the robustness of, for example, face detection to what you could call attacks or noise. But you have to know what type of noises you can be subject to, and somehow generate inputs that are realistic. This is a lot of information to have, and then you can have a test strategy in order to understand, similar to some of the things I've been presenting, the type of attacks that your DNN is vulnerable to by doing the type of applying the type of technique I've presented before, based on clustering, where you identify what are the conditions under which your DNN is vulnerable. So, for example, the DNN may be vulnerable when someone put her hands in front of her eyes, something like that.
My question is actually, it is not vulnerability, but let's say someone specifically designed such a way that it doesn't detect a face, like a specific person's face. So
Yes.
it is robust, it detects every face, but
Yes.
it is deliberately done that so it doesn't detect a single person's face. So that
Single person, yeah, but if you don't know who that single person is or why, the point of those strategies is to identify the conditions under which it doesn't work. And then if a person's face matches those conditions, well, but we cannot deal with specific instances because you have an infinite number of faces. So what we try to do is to identify the conditions under which it doesn't work. But those conditions have to be controllable by your simulator. So you are limited by your simulator, or you are limited by if you have a bank of images that you use instead of a simulator, you are limited to what's available in that bank of images. But we try to identify the conditions under which it doesn't work or it violates a requirement. So, that's more interesting than specific instances of someone's face, because we cannot deal with that. What do we do about that?
Thank you.
Right. Well, thank you very much. So it's 37 minutes past 2, so we passed 7 minutes, our scheduled time, but it's really good that people had questions in mind and there have been discussions. So that was actually the whole point. And I'm sure the members who couldn't make it today because of time differences or some other reasons, mostly because of time difference, I suppose, because in Central Europe and in other regions in eastern part of the world, it's nighttime, the evening. That might be the reason, but they will actually benefit from the recorded video because we have recorded the session, and our CSIM officers are going to post the video after editing. They'll post the video to YouTube, and the link is going to be shared and announced. So, Lionel, thank you so much. Once again, I really appreciate on behalf of the entire technical committee. So, everyone, please join me thanking Professor Lionel Briand for delivering this inspirational talk and which has been actually really very beneficial for all the members, and everyone in the committee is going to benefit. Thank you so much.
I can also share my slide. There are references as well. paper references, and thank you for your time and your many interesting questions.
Yeah, thank you very much once again. Thank you, everyone.
Cheers.
Cheers.
Bye.
Bye.